Hello. Good morning. I had some problems with my sound, but I think they are fixed now. And I may or may not leave this in the video for you to enjoy my voice softly talking about ridiculous things like the sound of the microphone. This is Math321 and 821, and that is my cell phone. Okay, so I'm back, and I'm still in two minds about whether or not to actually include all of these interruptions in the video. I guess I could, I suppose. The video production is quite low quality. I don't really do very much. I mainly use Blender and record the videos in bits and then chop out what I need. Anyway, okay, so I'm going to talk about this tutorial, which did not happen on Friday the 3rd of July. Turns out I'm really bad with updating the dates on things, and not particularly great at proofreading. In any case, this is on Moodle. You can have a look at it. This is an application of what we've been doing, and the application is to find the zeros of the function g of x, which I'm going to call g sine 1 over x. And we start off by considering the function f equals sine of x. Of course, we know the zeros of this. The zeros of f of x occur at the points multiples of pi. The first question is, why is this a bad choice for Newton's method? And if you actually go through the details and write down the formula, it should become obvious, and if it isn't, then please have a look at this, because this is important. Here's the derivative. The derivative of x is cos of x, and the derivative of x at pi over 2 is 0, which implies that the next iterate is undefined, in the sense that we can't work it out. The algorithm fails, so it's a bad choice. In order to work out how we could make good choices for initial iterates here and then use Newton's methods to find the roots, we can analyze what will be good choices here and convert everything, basically. So I'm not going to write down absolutely everything. I'm going to show you the steps, and then you can fill in the details as you need. So we know that the error for Newton's method propagates like this. So if you know the error in the kth step, we know what the error in the k plus 1 step is, based upon this, where xi, I always get it confused between xi and zeta, I guess, eta, not sure, eta and xi, are inside some appropriate interval defined by the iterates. Now, in this analysis, I'm going to assume that all of the iterates lie in a particular interval, and that is an appropriate choice. Well, I'm going to assert it's an appropriate choice. You'll need to check it, and later on when we do fixed point methods, there'll be a theorem which will allow you to work out if that's actually the case, which maybe I'll put in the next tutorial. In any case, in order for Newton's method to converge, we need to know that this, for convergence, let me say this, for convergence of the xi's, we need that the errors go to 0. We have this relationship, so I need the k plus 1 error to be less than the k error, and that requires understanding that this is small relative to the epsilon, relative to the k error, so this will be smaller and hopefully less than 1. Now, I'm not going to define strict bounds on this sort of thing. I'm just going to pick some bounds that work. That's fine. You don't have to do necessarily the best bounds possible. If your numerical algorithm works, then that's great, and if you can prove it, fantastic. And that's what this is working through. Okay, so in order to show that the error converges to 0, we need to show that this term has some upper bound, and then we can work out limits on this so that the whole thing will converge when we iteratively apply the method. So first of all, the first derivative is cos of x, and the second derivative is minus sine of x, and I'm going to pick some arbitrary interval. My arbitrary interval is the root at the kth root minus pi over 4 and the kth root plus pi over 4. So this is a small interval around the kth root, and if you look at sine of x, here's pi, that's pi over 2, and in between there is pi minus pi over 4, and similarly here. So we're looking at a little interval where the slope is well defined. It's not away from 0. I mean, so everything should work fine, and we can check this. So f dash of x applied to the interval is going to be a subset of minus 1 over square root 2, and f double dash applied to the interval is equal to minus 1 over square root 2, 1 over square root 2. How did I know that? Well, I plugged it into Mathematica, to be honest, but anyway, with special angles you can work out that this is the case. This lower bound can actually be improved, but it doesn't matter for our purposes, because what really matters is the smallest value, the value closest to 0. So yeah, that's why there's a subset in there, because I can't be bothered working out the actual lowest value. You can do it if you like. Right, so I want to find m so that for all x and x dash inside ik, I have the absolute value of less than or equal to m. That's what I'm looking for. Page 1. This is what I'm looking for, that bound. X dash x inside my interval ik, they have to lie inside these two intervals, so I can work out the upper bound fairly easily. So this will be biggest when the top thing is its largest value. The top thing is at its largest value at 1 over square root 2. And this term here will be at its largest when the denominator is at its smallest. This is the denominator here. The smallest is 1 over square root 2. And I'm ignoring the sign because I've got absolute values in here, so that's 1. That shouldn't be a surprise, because the derivatives themselves are cos and sine, and you know, well, maybe it should be a surprise. I did kind of pick this interval so that the bound would come out nicely. Anyway, so what this tells me is that epsilon k plus 1 is equal to epsilon k squared. So if epsilon k is less than 1, then epsilon k plus 1 will be even closer to 1. And in fact, you can prove with this, and in fact, the iterates will converge to 0. So that looks good, right? That's what we're wanting. Alright, now, so we have this ik, and I know that the root, this is an interval around my root. So if xk, let me say the iterate is inside my k, and I should not be mixing the k's here. This k is fixed, and that k varies, and I apologize for that. That's bad notation. In any case, so if xk is in that, then I know that xk minus xi minus the root is going to be less than pi over 4. That's less than 1. So if x0 is in, then epsilon 0 is less than 1, which implies that these things converge to 0, which implies that the xi's converge to the root in ik. Beautiful. So So that's an example of how you apply some of the theory that you've seen about the convergence of roots in Newton's method. Okay, so here's how you apply this kind of thinking to sine 1 over x. And there is some work involved in this. It's not just an inversion, though that inversion shows up in several places. A very simple graph of this function is that it kind of wobbles backwards and forwards and converges to 0, and there's an infinite number of roots in here, and that's because inversion takes infinity to 0 and 0 to infinity, so the real line ends up, you can think of it being swapped, and then you have to kind of crush in infinity number of points between 0 and whatever the sum value on the real line. As a heuristic way of thinking about it, that's fine. Okay, and in fact, if you take Taylor expansions around infinity, you do use 1 over x to do that. So there's a reasonable sense in which I just described as true. Okay, right. If we're going to apply Newton's methods to this, we have epsilon. Let me get rid of the k. Epsilon I plus 1 is equal to minus gamma dash zeta over g over eta I squared. So I need to bound this. G dash of x is equal to minus cos 1 over x squared. G double dash of x is equal to 1 over x cubed times 2 cos 1 over x minus sine 1 over x. Check it for yourself. Do the calculation. Make sure you can work out the derivatives. I expect you to be able to work out derivatives like this. Okay. So I now need to bound this. So let's do a trick. Let's say 1 over x equal to some variable y is an element inside my interval k. Why is this a good thing to do? Well, g of y equals sine of y. No. Say g of x is equal to sine of y. So g of x is equal to 0 if and only if y is equal to 2k k pi k inside the z integers. So it kind of makes sense to use this. With the substitution for y, g dash of x is equal to minus y squared cos y. That's a function that we can work out. It's much more reasonable to work out the bounds of this function on that with y rather than 1 over x. G double dash of x is equal to y cubed 2 cos y minus y sine y. I'm not going to show you how I work out the bounds, but basically working out the bounds involves taking each term here, working out what that term has bounds on this interval, and then multiplying the various bounds together and subtracting them as you need to, and so on and so forth. In any case, the result is that, and I'm not being particularly precise with the bounds here, I just need a bound. I don't need the bound. Well, I don't need the best bound, I just need a bound. Right, and remember, I'm doing this calculation with this thing, thinking of it as y squared cos y. Right, and similarly for the second derivative. the important points here are the important points are that is bounded away from 0. There's my bound. This thing is bounded away from 0. That's great. That means that my Newton method over this interval is well defined. Assuming all of the iterates lie in that interval, something I have not proven. So just watch out for that. And the other important point is that is bounded above by some k, and there it is, some constant. There it is. So this means these two facts imply that there exists some m greater than 0, so that g double dash for all zeta and eta inside my ik. Let's just put inverses on that, because of course I'm using y inside ik, not 1 over x inside yk. Right, so this means that I can write down I plus 1 less than m epsilon I squared, which is fantastic. It's really good. So if m epsilon 0 squared less than 1, then my errors will converge to 0, so Newton's method will work. I just need to choose my epsilon 0, small enough. So how would a generic version of this method work? Step 1, use bisect until some ei satisfies the relevant bound. Two, use Newton's method to converge the root. Hey presto. And the last point I want to make is that because I've really been thinking about this thing, this is really saying that x is an element of and the length of this interval. So I skipped this in class because it isn't really important, but in any case, the length of this interval is, sorry, that was the postman going past. I have no post today. K pi plus pi over 4 minus k pi plus pi over 4 divided by the product of these things, which is k pi squared minus pi squared over 4, and that is pi over 2 over k pi squared minus pi over 4 squared. So as k gets large, the length gets small, and of course at some point that length won't be representable in a computer and your numerical error will dominate the algorithm. We haven't calculated anything to do with numerical error here. Nothing. So, that's something you're going to have to worry about. Anyway, that's the tutorial, and I hope that made more sense.